and welcome to World Insight with me, Tian, coming to you from Beijing on CGTN. Today, we are bringing you Legends of the Unknown, a special program devoted to a breakthrough discovery of our universe, gravitational waves, and the great legends behind them. The true sign of intelligence is not knowledge, but imagination. Albert Einstein said that decades ago. Today, some of his imagination of hypothetical gravitational waves have been proved correct by a few intelligent minds who won the 2017 Nobel Prize for Physics. Not long after these physicists came back from the award ceremony in December, they flew to China and visited Beijing Normal University. They gave lectures and held discussions with China's science circle, the public, and students. They were encouraged and even a bit stunned by people's tremendous enthusiasm about their subject. In fact, they were hyper excited in China, both on and off screen. We will talk to them in a minute. Take a look at this first.
Standing on the shoulders of giants. In 2016, U.S. scientists for the first time announced their detection of gravitational waves, ripples in space and time hypothesized by Albert Einstein a century ago. Such a discovery represents a scientific breakthrough, opening the door to an entirely new way of observing the cosmos.
So these gravitational waves were produced by two colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago. They were detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is the most precise measuring device ever built.
In 2017, the Nobel Prize in Physics was awarded to 3 U.S. scientists for the detection of gravitational waves.
The Royal Swedish Academy of Sciences has decided to award the 2017 Nobel Prize in Physics with one half to Rainer Weiss and the other half jointly to Barry C. Barish and Kip S. Thorne, all of them members of the LIGO-Virgo collaboration. And the Academy citation runs for decisive contributions to the LIGO detector and the observation of gravitational waves.
A century ago, Albert Einstein hypothesized the existence of gravitational waves, small ripples in space and time that dash across the universe at the speed of light. But scientists couldn't find direct evidence of their existence until 3 scientists announced their direct observation of the elusive waves. To better grasp the process of their discovery, Tian spoke to 2 of them, Rainer Weiss, Emeritus Professor of Physics at MIT, Kip Thorne, Emeritus Professor of Physics at Caltech, and Chen Yanbei, Professor of Physics at Caltech, also joined the talk.
Welcome to our special edition of World Insight with Tian Wei. Sitting with me, we have 3 giants in their own field, in the field of physics. I want to start by asking the 2 Nobel laureates about how has been the process that you have gone through for LIGO and for gravitational waves. Where are we now, Professor? Concise and precise if you can.
Well, we've made an interesting discovery.
Yes.
But the process of making that discovery was a lot of fun for us. That's important. People don't recognize that why we get into this business is because it's a pleasure to work in physics. And for me, I'm an experimenter. And I happen to enjoy making things, and I enjoy seeing when they're working. And if they don't work, I enjoy trying to fix them. And then I enjoy the people I work with.
Right.
So the process is what's important.
The fun, can you describe it specifically?
The process is, yes. Every day you're working on something interesting. A circuit that didn't work, or a machine that you've made yourself, or somebody helped you make.
Right.
And you finally get it working right. And so you're very pleased with that. Or you're very pleased with the fact that maybe a computer program you wrote now suddenly works And it does explain what you're seeing. And that's what's going on day after day in that long, long time that did lead to this discovery.
Daily satisfaction for Professor Weiss, I would say. But what about for you, Professor Thorne?
Let me first say how long it was. Ray and I started working on the foundations for this a half a century ago. 50 years. It's been tremendously enjoyable 50 years. Of course, for me, it's not making a circuit work. It's trying to solve an equation. Or working with a student who's doing a great simulation and encouraging the student to do better, because the students do the greatest work. But it's the joy of working with colleagues, working with students, and, as Ray says, solving day-to-day puzzles that keeps you going on a day-to-day basis.
But I would assume 50 years, a lot of frustrations, because you are looking for gravitational waves. You assume something like that could exist, but yet only 50 years later that you found out it did.
No, you didn't get the point. I'm sorry.
What is the point?
The point
Go ahead,
is
Professor.
That's exactly, your reaction is exactly the one I worried about. And that is that people make it think, oh my God, we daily worry, we haven't detected anything yet. That's not what's going on.
What is going on?
What's going on is having fun with the thing you're working on that day. And that's the important part of this.
So is the Nobel laureate title important in any way to you?
No, not to me personally. It is important that for the general public throughout the world to have icons. That's true. Because the icons, in some sense, represent science, the beauty and the power of science. So we happen to be the icons this year. And so we may be able to use this somewhat to help influence science policy, for example. But neither I nor Ray had any desire for this Nobel Prize. Since we have it, then we'll try to make something useful from it. But let me just say that I knew approximately how strong these waves were. Ray didn't believe me. Well, he believed me at some level. He was.
I can see some interesting relationship going on between the two of you.
He believed me at some level. And I knew how fast they were working. And so I knew approximately when they would discover the waves. And, of course, my idea of when it would be kept evolving because I had to see how fast the experimental work was going. But by 2008, about 10 years ago, it seemed clear to me the waves would be discovered approximately 2017. And it came 2 years earlier. So we knew roughly where we were going.
What was the moment for you when that happened?
Well, for me, I woke up in the morning. I had an email from a young colleague saying, look on the web at an internal LIGO website where nobody else can look. You will see the data produced by a computer and the graphs produced by a computer that make it look like we have discovered gravitational waves. I looked, and it was amazing. It was too good to be true. So then there was a question that Ray and his experimental colleagues had to work very hard for several months to prove that this really was true by examining the instrument and the data.
But I would assume some of those moments happened before, that you were close to, the discovery, but eventually it didn't happen. So at the time when you were told, this might be it, were you calm? Were you just realizing maybe this is one of those many moments?
Well, once it looked likely that this was real, in my case, I just felt a sense of satisfaction. It was not exciting. It was satisfying because I had chosen to devote most of my career to trying to help Ray and his experimental colleagues succeed, and I had chosen to put my energies and the energies of Chen Yanbei and other students in directions that were fruitful, that had a very wonderful result.
Right. I want to go to Professor Chen a little bit afterward, but still I want to come back to you. From that moment that Professor Thorne was reading from the web, internal web, saying this might be it, to the time you eventually, together with your team, proved that it is it. During this process, how did you guys interact with one another?
Well,
did he pick up the phone every hour and talk to you and say, is it it? Is it already? What about now?
Well, look, it was a quite elaborate process. I mean, let's face it. And In fact, the experience that I had was I had been asked to go to the sites. The event occurred on a Monday morning, early Monday morning. And I was asked to go to the sites on a Thursday.
The sites are the locations where the detectors are.
I see.
And I was asked to by the guy, one of my students who now runs the project. I mean, the same kind of thing as Yanbei, Peter Fritschel, was a student of mine. And he's the boss. He says, Weiss, go down and take a look. What's wrong? Okay? And there's something crazy going on at the sites. And indeed there was. And I went and looked at it, and it turned out it was a particular problem. I told them it would take a week to fix it. They made a decision, let's not fix it.
This is just before the waves were discovered.
This is just before the discovery. And so I went on vacation to Maine. And I had the same experience that happened to Kip. I go to the web, and I see this thing I was told to look at. And my first instinct was, well, yeah, we always made blind injections. What are blind injections? We make artificial signals to test the apparatus and to test the people. And the thought was, well, this was just another blind injection. It looked, as Kip says, much too good. And, well, very rapidly people realized, no, it was not a blind injection. So then the next thought was, maybe we've been hacked. I don't know if you know what hacked means.
I guess I understand that.
I think you do. People from the outside had come in and made us look like a bunch of monkeys, and we're jumping around at their behest. And that was a big question that was started. It took a long time to get to the bottom of that one.
Right.
And eventually, some people did a very serious job and showed that, no, it was not hacking in the sense that you could prove that the apparatus had generated the signals. But you never could prove forever that it was not some even more ingenious hacker than you could think of.
But that hacker is more intelligent than anybody in the LIGO project.
That's right. I mean, that was the problem, just as Kip says. But, you know, you couldn't say zero. So eventually, and it took a while, that we came to the hypothesis that nature was an easier explanation of this than the hacker. And then people all over the project began to believe. But it took a while. And to some of us, and if Barry was here, he would say the same thing.
Right.
Barry Barish, the other Nobel Prize winner. Many of us became really much more convinced when we saw the second event.
I see.
And then the third one, and so forth. And then they became much more ordinary. And it became not this one singular thing, although it was a very beautiful singular thing.
Right.
It fit the Einstein theory beautifully and things like that.
Professor Chen, I remember the first time talking to you, it was not long after the gravitational wave was so-called discovered, and that was made news to the rest of the world. You were extremely excited as a young researcher about that fact. Tell me about your reflections upon your respectable professor's words earlier, and how do you see where we are today?
Well, I guess we're in a new era where we are using actual experimental data to study black holes and gravitational waves and other sources of gravitational waves. This is so different from the time I met Kip. I first saw Kip. He was giving lectures on general relativity.
Which was like 20 years ago?
Yes, 20 years, 17 years ago, when he was lecturing on general relativity and gravitational waves. I found these very fascinating. I liked the way we describe black holes, and when black holes collide, they emit gravitational waves. And also, Kip also works on the physics of the detectors and the physical processes that govern how the detectors interact with the waves and what governs the noise processes in these detectors. And he seems to understand everything, and then he can explain things very simply, in simple terms. I was fascinated. I thought, wow, I want to go into a field where there are different things I can study. And then, especially for a theory student, I can work on different kind of theory.
Yes.
And then, for me, for a long time, I kept working on the theory, the calculations. When the detection happened, it's a long, well, it feels not real at the beginning.
Just like what they said earlier.
Yes, and not only that, whether it is real, as in actual detection versus noise or hacking, but real in a sense like, I can't believe this worked out. The theory you describe black holes with, there's a horizon, and the black hole rotates, and then around the black hole, there's this curved space-time. There are mathematical equations. And now you're seeing these actual signatures from the black holes, and you keep thinking, wow, this is quite amazing that these formulas actually describe the black holes. So now you're confronting all the theory, which actually can be very abstract,
yes,
and with the actual experimental data that have very high significance, right? So now it's a new way of doing the research. Not only we have to do theoretical computations and think, but also to compare with data. And there's a possibility that the theories of physics that we have right now may not be complete. We could find new physics, or we could find new kinds of objects that we have not imagined before, or we find new understandings of these astrophysical systems. So
yes,
it's really a new way of doing research. And for me, it happened in the middle of my career, which is I'm really
quite
lucky.
lucky, right?
That's right.
It is really lucky. Yeah.
Yes.
I see a lot of excitement in your eyes when you were talking. And while you were talking, I was looking at the two professors looking at you. I saw some love and a lot of pride as well in this young researcher. Having said that, though, one of the things we talk about the future, it has something to do with the fact that these days people want to cash in. They want to cash in about scientific development as fast as they can. For example, they say, wow, new technology, artificial intelligence, we could cash in right now. We could build enterprises, we could go to the stock market. But what about gravitational waves? You guys tell beautiful stories. When are we going to be able to cash in? Kip, you want to talk about that?
Perhaps in about 3 centuries. Not much sooner. Ray thinks it's longer.
Yeah, I have a different answer.
Okay.
We're cashing in with our kids. We're cashing in with the excitement that we've generated in the society. And we're making it so that people, and it's interesting. I'll give you an example, which I was really quite struck by. A couple of weeks after we had made our announcement that we'd first seen gravitational waves, I was in New York City, and I saw an advertisement in the subway saying scientists have detected black holes in outer space. It's much harder to find an apartment in New York City that has a walk-in closet. Okay, and other things like that. In the popular literature, there was a statement of recognition of this kind of thing that we had done. Now, not that that was understood deeply, but the fact is, this has captured the society in an interesting way.
Very.
And we've got to use that as a way of making it so that they carry on with this. They carry on with understanding what the science actually is telling us. That is part of the human adventure. Look, that Einstein's equations fit so well. It's a human enterprise. I mean, Einstein was a fantastic person, and people knew that, but now here's further evidence to everybody.
Yeah.
And now the kids, every kid knows about a black hole. They don't know what it means, but they know black holes. And now you have talked with them about, they pay attention to you. Yes. And what you're doing is you're engendering a whole interest in young people.
I see.
Okay? That's the payoff, I think.
Rainer say cash in on the curiosity.
Yes, absolutely.
Kip, what about for you?
Well, I think, to me, the important thing is that we have opened up a whole new way to explore the universe. And it's a way that is not going to be important just for the next few years or the next few decades, but for the next few centuries. And that is truly exciting. When our descendants look back on this era and ask themselves, what did we get from the people who lived in the 20th and 21st centuries? I think a big part of that will be an understanding of the universe around us, an understanding of the laws of nature that govern the universe. And gravitational waves will be a very significant part of that as they look back.
We see national boundaries of technological research. We also see some of the so-called Cold War mentality still existing in our world today. What would that mean for a scientific research community like yours, even on the topic of gravitational waves, which would be only be able to cash in 3 centuries from now, using Kip's kidding words. But what would that mean to you as a researcher? Does it matter?
Well, for me, I don't think it matters. It did not matter for me.
No.
But let me tell an interesting story, which I felt is quite actually ironic, I guess. So I know some people from the Los Alamos National Lab, which is the national lab in the U.S. that does research in the nuclear weapons, I guess. And I also know some people from the Institute for Engineering Physics in China. And that's the corresponding place in China where they do nuclear weapons research. Well, they're like investigating how the two countries can eliminate each other. But the people who are doing this are not only friends, they actually go, from one place to the other for exchange. So they're really good friends. They have dinners together and they talk, and they're like, when I see these people are together, I feel it's kind of, I don't know what to feel, but that's an interesting example of what you talked about scientific research, understanding the nature. But I think the scientists are actually driven by the curiosity, trying to understand. We're not really driven by trying to serve our own. In many cases, there is no own government. I mean, serving our own government. We're really just driven by the curiosity. So we're, to some extent, research in physics was funded because governments feel like physics can help them build better weapons. That's very sad. On the other hand, we got this opportunity to study and try to understand the world, which in itself is not only interesting for us, but actually benefits the society. So it seems very complicated.
I think it is a very relevant story you just told. It is also a very warm story, I would say, in a way. Kip, you were involved during the Cold War. Exchanges with scientists coming from the USSR. At the time, it was former Soviet Union. Maybe many of the kids these days wouldn't even know what that is like. What's it like for you as a scientist, your experience and your ways of exchanging with your colleagues then?
So in my field of physics, in astrophysics, and also in technology for gravitational wave detection, Russia was very strong. It was, for me, the most interesting people to talk to and to collaborate with were in Russia and in the United States, and to some extent in England. And so I, immediately after I got my PhD, I started to move toward collaborating with Russians. I was first invited over by Yakov Borisovich Zeldovich. He was one of the two fathers of the Soviet hydrogen bomb.
I see.
And so I worked as a young physicist. I had been the PhD thesis advisee. My mentor had been John Wheeler, who was among the leaders in creating the American hydrogen bomb. I was working with the Russians who developed their bombs. It was similar to what Yanbei says. But we were working on problems in astrophysics, trying to understand the universe in a common manner, with a common culture, with a common set of tools. And these people were wonderful to work with. And it provided a human contact across what we call the Iron Curtain between the Soviet Union and the United States throughout the period from '68, when I started doing this, until the Soviet Union crumbled in 1991. And it was a marvelous experience, and I think it helped. I was able to help the two scientific communities come together and really see the world in a common sort of a way. So science can be a very positive force for reaching across international boundaries.
It could be, but you have to have a very strong mind, too, because I would assume at that time people would talk about you had a lot of exchanges with the former Soviet Union scientists, and he was the father, of the hydrogen bomb of Russia. And there would be suspicion. People would wonder, what did you exactly say? What did you do? And all of these things. So I would assume one has to have very strong mind in order to fight against all of these.
Either that or else a skepticism about the FBI and the CIA. In fact, so I had friends. Every time I would return, the FBI or CIA would ask my friends about me. And they would say, leave him alone. He will not cooperate if you ask him to. And his connections with the Soviet scientists are very important for, in some sense, for world peace, in some sense, for maintaining a human contact.
Yes.
And so they left me alone. I was never interviewed by the CIA or the FBI about these contacts. By contrast, my Russian friends were always interviewed after they'd met with me, always by the KGB, the secret police in the Soviet times.
There's an important lesson here, which is of a different kind. And as now even our field, the very small field that we just started, progresses forward, it has to transcend, has to get past the nationalism, because we can't do it alone. And for example, even this discovery, the LIGO discovery, was made by at least groups from 10 different countries.
That's right.
Okay?
That's right.
And now, when we look to the future, and what we would like to do in the future, namely build more detectors, bigger ones, ones that are more sensitive to some, taking the field, for example, we're in now into a field called cosmology, the field of cosmology, which is the field of looking at the universe in its entirety. That's going to cost a lot of money, and a lot of talent is needed to do that. And so it turns out we're now thinking very much so of that the next step in this, thing is going to be even more international. Has to be, because of the shared responsibilities and also the shared interest. And so I think, no, science, I mean, I know science has done bad things, it made bombs. Science also has this wonderful property of bringing people together and people working sincerely on common problems. And the fact that we're all looking together at the problem of the Earth warming up, that's going to be a bond that's going to pull the Earth together, even though it's going to cause unbelievable troubles.
Right.
We have to do this. And so, there's many pieces in the science where, as you look forward, it demands international collaboration. Yeah.
Yanbei, I also want to follow up on this to you. I mean, you see politics these days. Of course, none of you are politicians. You are scientists, physicists. But I do a lot of political discussions on my program every day. So you see this trend of so-called anti-globalization. You see this trend of looking inward rather than multilateral. You see only bilateral people. Some countries want to develop relationship rather than having multiple partners. All of this would have, one would argue, some impact on scientific research. So as someone in the community, how would you be able to insist on your ideal of having scientific exchanges, having as many ideas abundant as possible, being able to exchange with your colleagues from all different cultures and countries? How would you as scientists be able to do your part? I usually throw the most difficult questions to you because the other two professors, they have already answered it through their lifelong commitment. So,
we could do better.
All right, there we go. If we could come back to you
I
then.
guess one answer is to ask our Nobel Prize laureate friends to lobby for more global policy, I mean, from our government. But let me say that globalization is very important for science. I studied here in China until after finishing my undergrad research, and then I went to the US, where I was a graduate student, and then afterwards I went to Germany for 3 years. And then, so this kind of exchange between different countries is crucial for the growth of each individual student, and also the exchange are important for research projects, because the talents has to flow in a very free manner between the different countries across the borders. So it's very important. I hope that the new generation that grew up in the global environment, they would feel like it's quite natural to have a globalization. Like people, I guess these days people are less different than before, right?
That's
Kids
true.
at different countries, they all use their cell phone, and they watch the same videos, I guess. So maybe in the future where we could be going toward a better direction naturally, because I think the newer the generation, people actually they get sort of pulled into this global culture in an unknowing way.
Yes.
So maybe we shouldn't, I mean, I guess we should worry, we should try to, you know, lobby for better policy, but I think we may not have to worry that much because globalization is such a fast trend, it'll be inevitable.
Is that a good point, Kip?
I would basically agree, but I think the driving force, at least for scientists, is that the most interesting person to talk about some issue that is central to your research is usually in a different nation. And as a scientist, I know who the most interesting person or several people are. It was often in Russia. It was sometimes in England. It has been in China on occasion. But only a small fraction of the time in the United States. And so the globalization, the going international is central to making the progress that you want to make on your day-to-day work.
Yeah. It's just as simple as that.
It's as simple.
Without that, you just cannot function.
Yeah. Or you function in a much less effective way.
Yes, yes. Fine?
No, I'd like to say one thing.
Go ahead.
There may be troubles right now. I mean, obviously there's a trouble in our country with the way science is being looked at by the administration in the United States. I think that's a transient phenomenon. I would not look at that as a trend. I think it's a peculiarity that happened, and I'm willing to predict that this is not much longer than about the term of that administration. It really has to do with the fact that humanity is facing a global problem, and I said that earlier.
That's true.
And you can't solve that locally. You have to solve that as a problem that everybody is working on. Otherwise, you can't just let it happen in one country because it affects everybody.
That's just the way it is.
That's why the people have to come, and they know that.
Yeah.
And there's this anarchic thing that we have right now, which is a reaction to that, which I don't understand completely, but I guarantee you it's not going to be there for much longer.
All of you are beautiful products of education. You benefited from your growing up process. But now, here's the question. What kind of education
That's a good question.
would make the next generation, the one after the next, be genuinely interested in science, in the universe, and in the eternity of all these topics that all of you have been exploring throughout your lives? Let me go to you, Kip, first.
I think a central issue is to inspire nearly everybody if you can, throughout the world about the beauties of science and the power of science. That doesn't mean you successfully educate them about the details of science, but simply inspiring them and give them some sense of that, which is why I'm working in Hollywood. How else can I inspire 100 million people except by selling 100 million tickets to a movie?
So that's your remedy?
Well, that's one remedy. That's one remedy.
No, he's sincere about that. He said the same thing privately. He's been saying it for the last 4 or 5 years.
Yeah.
I mean, so no, he means what he's saying. I think that's
We're looking forward to you becoming a Hollywood star and
Well,
spread the message.
No star, but
Got it.
some great science fiction movies that really convey the message of the power and beauty of science.
Beautifully said. And Yanbei?
Oh, how to interest kids with science. That's very hard, actually. My daughter, I don't think she likes science. So it's really hard.
Does that have anything to do with you?
It could be. So I don't think everybody has to do science. She likes reading and she likes history. I think it's not, I think people should have some sense and they should have some logic and they should study well. They don't all have to like science. Like Kip said, I think people should have some general understanding of science and they should know that science does well. And we should also try to give people this way of thinking in a rational way. They don't have to be scientists, they don't have to have training, but they need to be not easy to be deceived by
Whatever
wrong
story.
That's right. By the So yes.
I think that's a great point. That Whether we are in the world of science or not, we need to be logical, we need to believe in evidence, we need to seek facts. Well, we need to also have a curiosity about what is going on in the rest of the world, and beyond probably the Earth. What about you, Rainer?
Well, I'm a strong believer in that you have to get at kids in high school and grade school, because they transmit the excitement that you might bring to a classroom. And I do this. I actually go to high schools and grade schools, and I enjoy that. And you bring things with you that make it interesting. You explain things like for how a rainbow works. You even show them pictures and make a demonstration of how things go. The more you can make it so it's their evidence, that they see it with their own eyes, the more they begin to believe, the more they begin to realize that there are ways of explaining things that are not just you're told, you find this out for yourself. And the thing is that that's the key, as far as I'm concerned, to getting an intelligent public. In other words, you make people so that they are willing to look at things for themselves and see, they get the evidence for themselves. Now, you can't do that with everything. But the other thing is really related a little bit to Yanbei, which I think that we do two things as scientists that could make a big impact on the society, and we still have lots to go. For example, this whole business of being able to think rationally means also you have to teach people a little bit more about probability. You know, the chance of something. How do you evaluate the chance of something? It's not just adding numbers. And, you know, we teach people in elementary school arithmetic and multiplication and all the tables and all these things we do by rote. We badly need to be able to teach young people how to evaluate the fact that if you have something happen sometimes and not other times, they can figure out what's the probability that it will happen in the future. You can do some calculations about that. And that's absolutely central to being able to have the people in the country realize why they have to worry about that they should maybe recycle, or they maybe should worry about whether they turn the lights off. Because, you see, they can now calculate maybe a little better that things they do might lead to changes that they don't know exactly will happen.
I can tell. Rainer and Kip have very different personalities. So you want to agree with?
Oh, I agree. I agree.
Well,
we tend to agree with each other. Rarely do we disagree.
Good for you. But you know, even coming here in China, in Beijing, with the Future Forum and also Beijing Normal University with the wonderful introduction of Professor Yanbei to be here in China, you see the excitement among the young people, the students here, and also the media as well. This is really something we rarely see before, Yanbei.
It was not the Nobel Prize, actually. Not only. There was the announcement of gravitational wave detection in the February of last year.
That's right.
And that was during the Chinese New Year's time. And then suddenly the news, became a big event, news event. And a lot of people are so excited about it. So I came to Beijing soon after and I gave a lecture, and I saw a lot of people very excited. I was really surprised.
I remember you said at that lecture, you said, I was surprised and I'm moved by what is going on here in China about gravitational wave.
Yes.
Amazing. Before we go, we have 40 seconds for every one of you. So what's next? You know, the journalists always ask the question, what happened? And then, what's next? So here comes the what's next moment. Let's go to you, Rainer.
You mean what's next in what we just discussed?
Yes.
Well, I think in our field, that's much more narrow than the things we've been talking about. We're going to open up a whole new field, as Kip says, and we're going to learn a lot about things we already know in a different way. Like for supernova, we'll know what they are by looking at them. We also will learn things that have never been seen before by this technique.
Right.
And that's the other part that's so exciting about it. I expect, and I think Kip does too, that we will make a kind of a revolution in our understanding of the universe with this new field.
Are you ready for that?
Yes, there are a lot of puzzles we have. Many puzzles. And maybe it'll solve some of those puzzles.
And many possibilities too, Kip.
Many possibilities, but what's next is the necessity for a big commitment to the development of the technology and the techniques and the instruments for moving forward and exploring the universe even more deeply in even more exciting ways than we have been doing. In gravitational waves, that means developing the techniques and the technology for the next generation of detectors, which could go into operation in the late 2020s or perhaps the early 2030s, with a very big improvement in what portion of the universe we can see and things we can discover. But the commitment to continuing the technological development, that's what's next, that's what's essential.
I got that. With a lot of fist on the sofa. Yes, there we go.
This is the theorist telling the experimenters what to do.
And Yanbei, what about for you?
Yeah, I just look forward to the opportunities to study new physics, new phenomena with the detectors.
Yes.
And then really not only doing the theory itself, but confronting theoretical computations with data and hoping for surprises that may come, will. Some surprises will come. We just don't know which one. I guess that's probability.
Probability. There we go.
Yes.
Chen Yanbei, Kip Thorne, and Rainer Weiss. What a pleasure to have the three of you to be with us. And thank you particularly to the two Nobel laureates for being with us. Really appreciate it. Thank you.
We enjoyed it. Thank you very much.
All the best.
Thank you.
All the best. Thank you. Yes. That's my discussion with Nobel Prize laureates for Physics 2017, together with Chinese young American scientists, enlighten us on gravitational waves, the universe, and their mission and the merits of education. We started our special program with a quote from Albert Einstein. Let's finish more words of wisdom. We cannot solve our problems with the same thinking we used when we created them. He said that, Albert Einstein, decades ago. I guess that is a great motto concerning both the discovery of gravitational waves and its pioneers. And with that, we are coming to the end of Legends of the Unknown, a special program of World Insight with me, Tian. And that is all the time we have for today. If you'd like to see more, find us, World Insight CGTN, into your search engine, or check out our YouTube channel. Follow us on Twitter, Facebook, and Sina Weibo. From me, Tian and everyone on the World Insight team, thanks for watching. Tune in again next time for insights across China and around the world. Good night.